You know, when you think about it, the modern world is literally built on chemistry. From the medicine that keeps us healthy to the tech in our pockets, it's really all one big story about our endless curiosity, our quest to understand and even change the very stuff that makes up our universe. So let's jump in and see how this all got started. And you know, this quote from Nobel laureate Roald Hoffman, it just hits the nail on the head. See, chemistry isn't just about a list of elements on a chart. It's about the endless, creative, mind-boggling things you can build with them. It's like being given the ultimate Lego set for the universe. But before we had the clean, white lab coats of modern chemistry, we had alchemy. It was this mystical, kind of secretive art form, and it was driven by two of the most powerful dreams humanity has ever had. So these alchemists, they were on this epic quest for two legendary things. First, the philosopher's stone. They believed it could turn cheap stuff like iron into pure gold. And second, the elixir of life, which was basically a potion for immortality. Now, spoiler alert, they never found them. But in their quest, all that mixing, heating, and experimenting, well, that accidentally laid the groundwork for the real science of chemistry. Okay, so while all this was happening in Europe, you've got to realize it wasn't the only game in town. Not by a long shot. Other cultures, especially in ancient India, were already way ahead with a seriously sophisticated understanding of chemical processes. I mean, just look at this timeline. It's pretty mind-blowing. We're talking about glazed pottery, a complex chemical process, all the way back in 2500 BCE. By 1000 BCE, they'd mastered metallurgy. But here's the real kicker. Around 600 BCE, a philosopher named Acharya Kanda was talking about atoms, an idea that the West wouldn't even touch for another 2,000 years. And this is where it gets really wild. Kanada's idea of paramanu was that everything is made of these tiny, eternal, indestructible particles that combine to make stuff. Sound familiar? It's the exact same core idea as John Dalton's famous atomic theory, but Kanada was talking about it over 2 millennia earlier. Just incredible. All right, so let's fast forward a bit. We're jumping over to 18th century Europe. This is the moment when the mystical art of alchemy really starts to transform into the rigorous, measurement-based science that we call chemistry today. Scientists finally started figuring out the fundamental rules that matter plays by. They came up with these 5 foundational laws, basically the rule book for all chemical reactions. And this was a huge shift. It proved that changing one substance into another wasn't magic. It was all governed by predictable, measurable principles. Let's meet some of the pioneers who cracked the code. And leading the charge was this guy, Antoine Lavoisier. Through some ridiculously careful experiments, he showed that you can't create or destroy matter. In any reaction, you end up with the exact same amount of stuff you started with. It just changes its outfit. Next on the scene is Joseph Proust, and he added another crucial piece to the puzzle. He found that a pure compound, say water, always has the same recipe. It's always the same amount of hydrogen and oxygen by mass. Doesn't matter if the water is from an iceberg or your kitchen sink, the recipe is locked in. Okay, so we have these rules, right? Matter is conserved, recipes are fixed. But why? What's the reason? Well, that's where John Dalton comes in and connects all the dots with his atomic theory. He said, what if everything is made of tiny, unbreakable balls called atoms? And that one simple idea explained everything. Of course, mass is conserved. The atoms are just rearranging. And of course, recipes are fixed. Compounds are just specific numbers of atoms sticking together. And just like that, Dalton's theory completely changed the game. It gave us a new pair of glasses to see the world. So let's use them. Let's zoom in from those big overarching laws and take a look at the actual building blocks of, well, everything. So all matter comes in 3 main flavors, and it all depends on how its particles are behaving. Think of it like a dance floor. In a solid, the particles are packed tightly together, frozen in place. In a liquid, they have some wiggle room. They can slide past each other. And in a gas, the party's gone wild. The particles are flying all over the place, filling whatever space they can. We can also sort everything into 2 big buckets. On one side, you have pure substances, like pure water or a bar of gold. Their chemical recipe is always the same. On the other side, you have mixtures, like the air you're breathing right now, or a cup of tea. Their composition can vary, and you can usually separate the parts out physically. So let's talk about those pure substances. What's their most basic fundamental building block? That would be the atom. Think of it as the ultimate Lego brick for an element. What makes gold gold? An atom of gold. Simple as that. And what happens when you start clicking those Lego bricks together in a specific way? You get molecules. A molecule of water, for example, is always two hydrogen atoms snapped onto one oxygen atom. This is the secret right here. This is how we get a universe of infinite variety from just 100 or so types of atomic bricks. Okay, so this is all great. We've got atoms, we've got molecules, but there's a huge problem. Atoms are ridiculously tiny, and there are billions and billions of them in the tiniest speck of anything. So if chemistry is all about combining them in exact ratios, how in the world do you count them out? No, really, stop and think about that for a second. It's a real head-scratcher. You can't just pick them up and count 1, 2, 3. You can't put one on a scale. It seems completely impossible. But the solution chemists came up with was actually brilliant in its simplicity. The solution was an idea we use every day. When you buy eggs, you don't ask for 12 eggs, you ask for a dozen eggs. Dozen is just a convenient word for a specific number. Well, chemists realized they needed their own version of a dozen, but for atoms. And in chemistry, that special counting unit is called the mole. That's it. It's the chemist's dozen. It might sound a little weird, but this one concept, the mole, is the absolute bedrock of all modern chemistry. It's the bridge between the invisible world of atoms and our world of things we can actually weigh and measure. So you're probably wondering, okay, a dozen is 12, so what's a mole? Well, brace yourself. 1 mole of anything contains 6.022 times 10 to the 23rd particles. It's a number so massive it's hard to even wrap your head around. But it's this exact number that lets a chemist weigh out a powder in grams and know precisely how many atoms or molecules they're dealing with. It's pure genius. All right, so we've been on this incredible journey, right? From alchemists dreaming of gold all the way to understanding atoms and this thing called a mole. But, so what? Why does any of this matter in our lives today? Well, because mastering these ideas is literally how we build and shape the world around us. Well, this is why it matters. This is where it all pays off. Because we understand how atoms combine. And because we can count them with the mole, we can design life-saving cancer drugs. We can create the optical fibers that make high-speed internet possible. We can invent safer chemicals to protect the ozone layer and build the massive industries that fuel our entire economy. So when you look at it that way, this whole story, from a mystical dream of turning lead into gold to the precise science of the molecule, it's really a story about us, about our relentless curiosity and our incredible power to reshape reality.